Dear students, this is the fourth video dealing with partial differential equations. In this video, we will have solution of one-dimensional wave equation. In the last video, we have already seen how we derive one-dimensional wave equation. The equation is dou square u by dou t square is equal to c square into dou square u by dou x square. We call it as one-dimensional wave equation. Now, in this video, we'll learn how we'll solve that one-dimensional wave equation, one-dimensional wave equation. Okay, so one-dimensional wave equation with the initial and boundary conditions. In the last video, we have seen only this much. Dou square u by dou t square is equal to c square and dou square u by dou x square equal to 0. But the entire description of the problem requires initial conditions as well as boundary conditions. So these are the initial conditions. That means at time t equal to 0, that's why it's 0, 0 here. You know u is a function of x as well as t. At t equal to 0, initially it was f of x. That means you may be remembering that figure where we release the string with a force. That force is here x. That means at each point x from 0 to L, this is, if it is 0, u0, 0, it is f of 0, ul0, it is f of L, like that. So it is defined by this function f of x. So initial value of the x distribution is given to be ux0 equal to f of x. That's the second condition. Now initial velocity is taken. That means dou u by dou t when t equal to 0 is taken to be g of x. That is also a function of x where t is not relevant there, because we have differentiated this with respect to t, and we put t equal to 0. This is what we call as initial velocity. So these two things are called initial conditions. And now this is true for all x belongs to 0 to L. You know, we take the string of length capital L. Now we have two boundary conditions. It says that if you remember, the string is not vibrating at x equal to 0 and x equal to a. That means endpoints a and endpoints b remain always not vibrating. Not vibrating means u is actually amplitude. Amplitude will be 0 at a and at b. So this is the value of at b, this is the value at this a. So this is true for all t, means for all the time it is not vibrating. That's why we have taken it as t from 0 to infinity, u0 t equal to 0 and ult is equal to 0. So these are the two boundary conditions. So the equation together with these two initial conditions and these two boundary conditions all together we call it as one-dimensional wave equation. Okay. Now there are two different methods for solving one-dimensional differential equation. One is D'Alembert's solution. The second one is method of separation of variables. This we will learn in the next video. Today we will have a description of the D'Alembert's solution. Okay, D'Alembert is a mathematician who solved this, who used this method for solving one-dimensional wave equation. So before solving the equation, once again you have to remember all these equations. This is wave equation, these are the initial conditions, and these are the boundary conditions. So let's move on to D'Alembert's solution. In this method, we introduce two new variables v and w. Already there are variables u, x and t. Instead of x and t, we will use v and w now onwards, where v is actually x plus ct and w is x minus ct. So that means two new variables v and w are introduced. V is x plus ct and w is x minus ct. What will be derivative of v with respect to x? That will be 1. Derivative of v with respect to t will be c. Remember, vx is equal to 1 and vt is equal to c. Similarly, wx is 1 but wt is minus c. Okay, with respect to t, if you differentiate, x will be constant, therefore its derivative is 0, and with respect to t it is 1, actually it is minus c into 1, which is minus c. So these four values we have to remember, which we will be using in the next computation. So vx is equal to 1, vt is equal to c, wx is equal to 1 and wt is equal to minus c. Now we transform the wave equation, which is there in equation number 1, into new variables. Already u is there, v and w are newly introduced variables. So we convert u, x, t in terms of into u, v and w. So we will have a differential equation involving u, v and w, partial differential equation involving these three variables. Using chain rule in partial differentiation, you can differentiate u with respect to x as u with respect to v into v with respect to x plus u with respect to w into w with respect to x. You might be remembering this in the partial differential methods. So it is dou u by dou v into dou v by dou x plus dou u by dou w into dou w by dou x. Therefore vx, as I told you, it is 1 and wx is 1. Therefore it will be uv plus uw. Now you differentiate this once again. For differentiating once again, you have to differentiate. This is actually, remember, this is the function of u, v and w will be here. So again we have to differentiate this with respect to v into vx plus the same thing with respect to w into wx. Wx, you know, it is 1, vx is also 1. Therefore this should be differentiated with respect to v, means uvv, that means second derivative of uv with respect to v plus uwv same as uvw. Similarly uv w, which is but there uww. Therefore this can be combined to get it as 2uvw. Therefore uxx in the partial wave equation can now be replaced by uvv plus 2uvw plus 2uww. So that's the value of uxx. Similarly, you have to find out utt. For finding utt, first you have to find out ut. Ut means uv dou u by dou v into dou v by dou t plus dou u by dou w into dou w by dou t. Therefore vt, as I have already mentioned, it is c and wt is minus c. Therefore c can be brought out, so it will become uv minus uw. This should be differentiated again once again with respect to t. So as we did in the previous case, this should be differentiated with respect to v into vt, that's c again. This is again differentiated with respect to what? I have here also there must be c. So this must be differentiated with respect to w into derivative of wt, that is minus. So c into c, here also c into c will be c square coming outside. Then as in the previous, it is uvv minus uwv. Then here it is again there is a minus, so it is minus uvw plus uww. Therefore it is uvv minus 2uvw plus uww, that's c square. So for utt is c square and uxx is as in the previous value, it is uxx is like this. So we'll go to what is the equation number 1. That's your wave equation. Wave equation is uxx is equal to, utt is equal to c square into uxx. Therefore this is your utt. This is c square, and that is the c square in the partial differential equation, wave equation. This is uxx actually. Therefore c square and c square will be cancelled. After cancelling c square, uvv will be cancelled from both sides. Similarly uww will be cancelled. Therefore minus 2uvw is equal to 2uvw. Take this minus 2uvw to the other side. Therefore 2uvw, again 2uvw will become 4uvw equal to 0. Therefore 4 is not equal to 0. Therefore uvw equal to 0. So this is a simpler equation, simpler than the previous wave equation. Therefore this is what we call as canonical form. Remember, this is what we call as canonical form of the wave equation. Canonical form. After the substitution of v equal to x plus ct and w is equal to x minus ct, this is what we get. This is very simple to solve. We will see how to solve it. To find the solution of u in terms of v and w, we first integrate with respect to w. So remember, this is derivative of u with respect to v and w. So to get eliminated w, we have to integrate this with respect to w. But remember, when you integrate with respect to w, v will be constant. Therefore, if integral of this will become a constant, that constant will involve v. Therefore, that's thing that we take it as phi 1v. Therefore, uv, when you integrate, w will go. So it is uv is equal to phi 1v. Now again, if you integrate with respect to v, keeping w as constant, this v will go. You will be getting u, which is equal to integral of phi 1v with respect to v plus a constant. That constant may depend on the constant variable w. So it is. This is again a function in v. We take it as phi of v plus phi of v. So that's phi of w. Therefore, u is equal to phi of v plus phi of w is a solution of the wave equation, but we have taken v as x plus ct and w as x minus ct. Therefore, uxt is equal to phi of x plus ct plus phi of x minus ct. Call it as equation number 6. Therefore, this is a solution, but we have to find this phi and psi in terms of the functions f of x and g of x. F of x is the initial condition, initial x distribution. This is the initial velocity. Using these two values, you can find phi and psi. Phi and psi are arbitrary. It may be sine, it may be cos, whatever it is. But it should be, the variables must be x plus ct and x minus ct. But now we will calculate phi and psi in terms of f of x and g of x, which are described in equation 2 and 3. How to do it? What is f of x? F of x is actually ux0, initial value of x's when at time t equal to 0. Ux equal to 0 means you have to put xt here 0. Therefore, ux0 will be equal to phi of x plus 0, that is phi of x plus psi of x. Therefore, f of x is equal to phi of x plus psi of x. We call it as another equation, equation number 7. Now we have now second condition is actually utxt is equal to g of utx0 is equal to g of x, but you have to differentiate this with respect to t. Therefore, utxt will be equal to phi dash x plus t, phi dash x plus t into derivative of this with respect to t is c, and psi differentiate means psi dash, derivative of x minus ct is minus c. Therefore, c and c is common. So it is phi dash x plus ct minus psi dash x minus ct. Now here you put t equal to 0. T equal to 0 means utx0. Utx0 will become g of x, and the other thing will become, when you put t equal to 0 here, t equal to 0, this will become simply phi dash x and minus psi dash x. Therefore, c into phi dash x minus psi dash x is equal to g of x. Therefore, you can divide this c. C is not equal to 0. You can divide by c. Phi dash x minus psi dash x is equal to 1 by c into g of x. Now, in order to get phi x minus psi x, you have to differentiate. This is derivative of phi of x minus psi x. In order to get the difference of phi of x and psi of x, this is actually derivative. To get rid of this differentiation, you have to integrate. But we integrate between x0 and x, where x0 is an arbitrary value of x. Therefore, phi of x minus psi of x between x0 and x, that is the integrated thing here. On the other side, we have to integrate g of x actually, but to integrate this x will be replaced by some another variable s. Then we integrate with respect to s between x0 and x. So it is 1 by c integral x0 to x integral g of s ds. So putting x first minus putting second x0 that we have taken to the other side. So we'll be getting phi of x minus psi of x. Here actually it must be minus of phi of x0 minus psi of x0 that I have taken to the other side. Therefore, you'll be getting phi of x minus psi of x is equal to 1 by c integral x0 to x g of s ds plus phi of x0 minus psi of x0. That is equation number 8. Now look at equation number 7. Equation number 7 is actually giving you the value of phi of x plus psi of. This is here is sum, and equation number 8 gives you difference. When you have sum and difference, if you add plus psi x and minus psi x will be cancelled. But we will be getting the value of 2 phi of x. So on adding, you will be getting 7 and 8 are added means, and dividing by 2 will be getting phi of x. That is equal to, on the other side, if you remember, here in the equation number 7 we have f of x. On the equation number 8 we have this expression. Therefore, f of x added with this one and divided by 2 will be the so it is 1 by 2 f of x plus 1 by 2 c integral x0 x to x g of s ds, plus that if you remember phi of x0, this is actually the side in the equation number 8. This is the in equation number 7. So equation number 7 in equation number 8 divided by 2. That divided by 2 is here actually. These are the divided by 2. So this is the value of phi of x in terms of f of x and g of x. This will be cancelled later. We will see how it can be done. Similarly, when you subtract 7 and 8 and divide by 2, you will be getting the value of psi of x. So it is this is the right hand side of 7. We will divide by 2, so it is 1 by 2 minus this is the right hand side of 8, so 1 by 2 that you call it as 10. So we have now phi of x and psi of x. Remember, you have this equation number 6 where u of x is in terms of phi and psi. Phi of x we know. Similarly, psi of x we know. So what will be phi of x plus ct? Instead of x we will be writing x plus ct, and in psi of x we will be replacing x by x minus ct. Therefore this is phi of xt x plus ct plus psi of x minus ct will be the value of this from equation number 9 will be taken. Here is phi of x. Therefore, replace x by x plus ct. You already get phi of x plus ct will be equal to 1 by 2 in f of x plus ct, 1 by 2c x naught to x plus, wherever x is visible, you replace x by x plus ct. Therefore, x naught to x plus ct. Here there is no, this is a constant. So x naught is also constant. Therefore, you will be getting it like this. Phi of x plus ct plus psi of x naught. This is f of x plus ct by 2. That is the part of phi. Psi of x minus. This is the part of this is the part of phi, and this is the part of psi. You will be getting f of x plus ct plus f of x minus ct by 2, and the integral actually there. The other part will be cancelled. Which one will be cancelled? This part will be cancelled with the, because this is minus, and the previous one will be plus actually. Therefore, they will be cancelled on addition. So they on cancellation. So integral are in difference. Remember, it's x naught to x plus ct. This is x naught x minus ct. So we can split this as x naught x minus ct plus x minus ct to x plus ct. Therefore, this and this will be cancelled. The first part, so it will become x minus ct to x plus ct. Therefore, final solution is actually uxt is equal to f of x plus ct plus f of x minus ct by 2 plus 1 by 2c integral x minus ct to x plus ct g of s ds. This is the final solution given by D'Alembert. So this is what we call as D'Alembert solution of one-dimensional wave equation. Thank you for watching. If you have any doubt, you can ask me.